Usual
Sure.
question. Yeah.
Sure, sir.
No problem. Right. We'll start from we finished it yesterday again. I tend to do it that way. I tend to start with questions where we finished, and then work our way back a bit, and then jump through. Start where we finished ages ago. So it's always see what's fresh in your memories. Okay, so we finished yesterday with engine inspections after heavy landing and lightning strikes. What would be a typical sign of a lightning strike on an aircraft? On the engine cowlings and engines, what might you see?
Dark spot.
Yeah, it keeps sort of burning spots. Yeah, what else? If you remember from the module 17,
pitting.
Yeah, pitting. Yeah, so actually holes. You know where the electricity's hit in there and burnt it, melted it. Remember from module 17, we had the propeller blades. It had a lightning strike with holes in there. Again, same for fuselage. You might see some there. You might see damage within the actual engine. If you do suspect a lightning strike, what sort of tests might you be carrying out on the actual engine, as well as a visual inspection?
We have to take it to the hangar.
Yeah, get out of the thunderstorm first. Make sure you're safe first before you do anything. Yeah.
Then we have to check the engine bearing.
Yeah. So yeah, you might do a rotation. So actually spin the engine by hand. Don't use the starter motor. Just spin the LP compressor first. That'll spin the LP turbine. If that sounds okay, good. They get a turning tool. Put it on maybe the gearbox. So that'll be for HP spool. You can spin that. Make sure that feels free for move. So basically what you're checking is, depending if it's a twin spool or triple spool, you're checking for free movement. There's no untoward noises or restriction. It feels good. If it feels okay, then yeah, go and have a look inside, get a borescope equipment out, go and have a visual inspection inside, make sure everything's okay. And what about the oils and bearings?
Yeah, excuse me?
How about the oil system? What would you do with the oil system?
For the oil system, we have inspect the oil filter as well as chip detector.
Yeah,
and then
yeah.
It is recommended to do SOAP, S-O-A-P.
Yeah, good soap sample. What does SOAP stand for?
It's something like James Bond movie.
Yeah, James Bond. Spectrometric, that's what we call it. Spectrometric oil analysis program, yeah. Soap sample, yeah. Okay, so remember, a soap sample, oil sample will be sent away. We will burn the the oil if they suspect any bearing damage, and if there's any bits of bearing there, that will burn off. And again, the wave light given from the heat, the light when it's burning will be specific to that material, and they can check it against the graph and say, yes, maybe there's some bearing material from the front bearing or a cage material from the rear bearing, whatever it is. They can determine, yeah, it might be worth pulling the engine, or it could be fine. Yeah, it could be fine. And again, you do those checks as required until you're satisfied. So they might say, if it looks okay, we'll check it again in 3 flights time or 20 hours time. We'll do another check, make sure it's fine. If it's not, then yeah, you might look at changing the engine. Depends on the severity of the lightning strike. If it's had multiple lightning strikes, there could be a lot of lightning strikes can polarize a lot of parts within an engine, which makes it magnetic. That can cause problems. Electric wires can fry out and everything. So yeah, just apart from the engine, you've got the whole aircraft to worry about as well. But yeah,
But most of the time, a static discharger is gone.
Yeah, usually, yeah. Yeah, that's it. You don't have to worry about that. Don't worry about fuel flow and static discharge. As long as you're not touching the aircraft. Okay, so that was lightning strikes. Heavy landing. Again, so heavy landing is going to put a lot of stress on engine bearings. So again, you'll be checking probably oil. Again, freedom of rotation, making sure everything's okay there. Attachments, the thrust struts, checking for bows and members. If in doubt, you might have to actually remove the engine. It could put too much stress on the pylon cowlings, the fuses, checking for fuel.
What about the fuse? If it is
heavy, yeah, that would definitely be a massive check in there. Maybe one fuse might have gone, there could be, or it's cracked. And that's what happened once before. There was a crack on a fuse. There was a big incident back in Amsterdam many years ago where a 747, it lost its number 4 engine. It fell off. And as it, so number 3 engine first, it came out, flew forward, and then hit number 4 engine, took number 4 engine out, and they crashed into a built-up area. Unfortunately, many people were killed, and that was a fuse. It'd been vibrating, snapped, so I put a weak point on it, and it just let the rest of them snap off as well. So yeah, many checks on that one. If it has been suspect, then rather than just say it might be okay, it'd be remove it, replace the fuse bolts. Okay. Again, NDT checks, visual inspection first, NDT check, and if you suspect it, it's been quite a heavy load, there's a good chance the fuses could be stressed. Okay, yeah. Any sort of examination, visual inspection, whether it's combustion chambers, turbines, compressors, whatever you're checking, what else would you do? If you find some damage, what would you do?
We have to do NDT boroscope.
Yeah, so you've been using boroscope equipment. You found say you found a crack on a turbine blade. What would you do?
We have to record the damage, and according to that, it will be inspected further. Like it will be continue or to replace it. Yeah,
that's it. You just got to check is it within limits. If you're unsure, get a second opinion, get a fresh set of eyes, because sometimes using boroscope equipment, your eyes get very focused, and you have to sort of refresh, and you start doubting yourself. Unless it's very obvious damage. Sometimes if it's one of those bits where you're not quite, is it a crack? Is it just a bit of dirt? Get somebody else to have a quick look, it's just a bit of dirt, or no, that could be a crack. And if they're doubting it, well, there's a good chance it is a crack. If both people, or even 3 people, are thinking it might be a crack, pull it. Better safe than sorry. But the main thing is, any damage you find, especially combustion cans, record the damage you find, or not find. If you don't find anything, fine, that's great. If you do find anything, make sure you record the position, because it could be multiple can engine. Probably not the ones you'll work on, you'll just be an annular can. But if you're working on a multiple can type combustion system, you say maybe number 3 combustion can, inner lining at 6 o'clock position, times 3 cracks found to be 20 millimeters, or around the cooling ring or something like that. So the time, the date, the location, what you were using, and the actual amount of damage you've found. And then if it is in limits, it's okay. At least it's recorded. So if there was an incident later on, well, that was recorded, it has progressed, and also you can change how quick or how many times you check that, because it might have been a 50-hour check, and now, because they found a crack, it now reduces it to a 25-hour check. And if it's getting worse, 10-hour, 5, and so it all depends on the manufacturer's instructions. But we do find damage, it's within limits, we will want to monitor that damage, because we try to keep that engine in as long as possible. Good old money. But yeah, we can keep every aircraft that flies has got lots of damage on it. That's the problem. If everybody that flew an aircraft, or the passengers, knew how much was wrong with their aircraft, they probably wouldn't fly an aircraft, because there's always lots of things not working, broken, cracked, needing repair, but won't be repaired until maybe the engine is removed. And then it's access to be able to repair that. All within safety. It's always in safety. There's always damage there's always safety limits, but we need to keep checking it, maybe more in a quicker schedule as well. Okay, but yeah, you'd be surprised how much an aircraft has got wrong with it. But it's all within limits. That's the problem. Okay, good. So keep an eye on things. When you're taking blanking plugs out for doing borescope inspection, endoscope inspections, again, make sure you apply the right anti-seize compound, and you also torque tighten it. The amount of times I've gone out to an engine, it feels like some gorilla has put the blank back on. They must have been hanging off a massive 6-foot bar. There's no reason you use a torque wrench. Tighten it, torque it, done. But some people would just put a big bar on it, so the tighter the better, which when you come to take it off, it strips the thread, and you have to go and replace the helicoil. So again, proper lubrication, anti-seize compound, and always torque tighten appropriately. And never do it when it's hot, because 1, it burns your fingers, and 2, it won't fit properly. Okay, what was the 4 types of view for a rigid probe assembly? So the 4 views.
A straight view.
Yeah.
Lateral, oblique, and retro view.
Good. The probe itself, optical instrument, it has to perform two functions. What was the two functions?
Display a sharp
Yeah.
image.
Undistorted image to the eyepiece. Yeah, nice, basically a nice clear image. And also
direct a beam of the light for illumination.
Okay, so you put a probe in there without a light, you're not going to see much at all, just be darkness. Sometimes, so if your light fails, depending on what you're looking at, maybe in the HP turbine, IP turbine, depending on where the position of the engine is, you might get the light, the sunlight coming in, and that can sometimes help. So sometimes you don't need the light, but most of the time you do need a good source of light. And look after the probes, make sure the lenses aren't scratched, because if that's scratched, that makes your vision all go funny and it's not nice to look at. So yeah, always keep them clean as well. Okay. Right. Engine mountings. Again, you'll be doing things like checking for cracks, corrosion, dents, bowing, all that sort of stuff. If you do find a crack, what type of test should be carried out?
Crack check.
Crack check, yeah, crack check. So what that crack check? What does that include? Magnetic flow test. Yeah. It's a part of a non-destructive testing. We used to use dye penetrant for certain crack tests. Now, magnetic flow we'll put a special layer on there, and that's using a magnet. And if there's any crack, that will distort the field of these little filings and that sort of thing. As well as doing PDF, PD4, PD5, not in the books. It's just a dye penetrant which can be used as well. And you can also use various other types of non-destructive testing if you suspect it. If you suspect it, not sure, take the engine out, unfortunately, and then maybe replace the mount, if required. If it's one of those, we're not too sure, well, in that case, if you're not too sure and the supervisor's not too sure, then there's a good chance there's something not right. Okay, unless you're 100% positive, it's fine, take it out. Better safe than sorry. You don't want engines falling off in the sky.
Most of the time, we do dye penetrant test because it's cheap.
It's cheaper, yeah. There are some dye pen tests are good for certain parts, but sometimes you have to do X-rays as well, and also the magnetic flaw ones, where it's more appropriate because certain shapes of certain components, like welds, dye penetrant's not very good in sort of weld lines, because you might need a magnetic type to actually prove if it's a crack or not. We've got a component, I think it was an FCOC on one of the welds. It looks like a crack, and I swore it was a crack as well. It was like, it really looked like a crack, but we were two minds about it. We put some dye penetrant on it, and it wasn't. But it's just a very deep score. But again, a score's not good either. It just showed you, but it looked like a hairline crack. But it was just a very deep score. But again, a score is a weak point, and that could potentially lead to a crack. So again, if in doubt, take it out, as I say. Good. Right, oil systems. You'll be checking your maximum minimum oil consumption. So again, when you put it on your books, you check the record. If you get a spike, remember that's probably just unfortunately somebody's forgot how much oil they put in and they just put a random figure in there. It will happen. It will happen. You'll be tired of night shift. You'll say, oh, Ganjera, how much oil did you put in the engine? I went, I think it was 2 litres. Okay, thank you. And it was maybe just 1 litre. Okay, so if you ever see a spike in your oil charts, it's probably just a random figure put in. It's when you see it start to trend higher and higher and higher consistently, then yes, the engine's going to be using more oil. So again, they do a performance check, checking the leaks, and checking power, etc. if required.
Or we can check from cockpit.
Yeah, if you've got a gauge, yeah, that's an easy one. You need to check the gauge is working. Yes, some of the commercial, obviously, I've never had the pleasure of working commercial aircraft. It's always been fighter aircraft. But we never had gauges in the cockpit. It was always on the actual engine. The ones we had were a drop stick. So underneath the oil tank, you would do 90-degree turn. The stick would drop down. It's got a magnet on it. Now there'd be a float in the oil tank, which obviously goes down and up with the oil level. And then the magnet on the stick would obviously, when the float matched up with the magnet would stick, and then we'd read off the increments. It was in litres we had. But you might have a drop stick, like a car, a motorbike. You might have a sight glass, or you might have gauges in the cockpit. Yeah. Right, turbine exhaust. If you find any deposits in the exhaust system and they're white and silvery splatters, what does that possibly indicate?
Aluminium.
Aluminium, yeah. If it's bright blue or golden speckles?
Titanium.
If it's very black and sooty?
Carbon deposit.
Yeah, just normal. If it's black and sooty, it's a carbon coming out. If it's really, really black and sooty, it's probably a mixture problem. Okay, again, I keep using the cars and motorbikes. You check exhaust. If you've got a lot of black smoke coming out, yeah, you need to check your mixture. If you've got white smoke coming out, your cylinder head gasket's gone. Okay, but you don't have cylinder head gaskets on jet engines, unfortunately. Anyway, digressing there. Okay, yeah, we're going to come on to compressor clean shortly. Compressors, look at the damage. We can do what's called compressor washing, which we're going to cover shortly. It does mention it in the previous chapter. But you can clean some compressors by using a mild abrasive. Again, we're going to look at that later on. So don't worry too much there. But there was 3 types of compressor damage were classified as. What was the 3 classifications? Or assessed as?
Superficial damage.
Yeah.
Impact damage and repairable damage.
Yeah, good. And as I said before, most inspection, most of the check, it's common sense. You know, you look at the dents, cracks, nothing. If it doesn't look right, it probably isn't right. You know, and so it's a lot of it is common sense. But again, you just always follow the manual, and anything you find, record it. Always good. Good. Okay. Maintenance overhaul. That's fine. What was flat rating?
Engine operated in high performance with temperature.
Yeah, and with ambient, over a wide ambient temperature range. Oh, excuse me. Yeah, it refers to the flat shape of the field power curve and the point on ambient temperature scale at which the power starts to drop below 100%. So that flat line was a guarantee that within the example we've had was up to 32 degrees. That's just an example for that one. As long as the manufacturer will guarantee that amount of thrust within that temperature range up to that point there. Anything above that, there will be power, but not guaranteed if you're outside that. So that's what your flat rating. There's always a little bit extra available, but it won't always be guaranteed because the temperature might be too hot then. So that's when the pilot was doing his calculations for takeoff. He's got his weights, his passenger weights and all the fuel cargo weights, temperature and pressure of the day, set your thrust gauge, set your EPR gauge, that's how much thrust I need, and his graph, and he knows the distance of the runway, then he should be able to calculate, yes, I've got enough room or length of runway to take off. But sometimes it happens where it could just be too hot a day, and for the type of runway, they might not be able to take off. They might have to wait till the morning for a cooler air to get the thrust. Okay, because remember, the engine will show you the speed of the engine, but that doesn't necessarily mean you've got the thrust from the engine. Yeah, like we said yesterday, going for a run on a cold day and going for a run on a hot day you run out of breath very quickly, and a cold going the same speed as you would do on a cold day. Okay, so the engine needs to breathe healthy as well. Okay. Horsepower, what was indicated horsepower?
Theoretical power.
Yeah. Brake horsepower. Yeah, before the loss of gearboxes, etc. Drivetrain. Shaft horsepower.
No one. Propeller power delivered to the propeller shaft.
Yeah, propeller and rotors of a helicopter. And what was the typical losses percentage?
10%.
Good. Okay. Right, specific thrust will indicate what compared to something else? You've got specific fuel consumption and another set of figures for an engine that is useful to know. It's called specific thrust. And what does that compare?
It compared the efficiency of one engine to another engine.
Perfect. You must be reading it out of the book. Good. Okay. Thrust, acceleration and an engine can also be, as well as forward, it can also be so acceleration. You can have it forward. It can also be
rearward.
Yeah, rearward. Yeah, forwards and backwards. And as usual, thrust is felt where?
All rotating and static part.
Yeah, that's it. Good, good, good. Right, we'll leave that bit for the moment. Okay, so the last bit is efficiencies. Thermal efficiency and propulsive efficiency. Thermal efficiency was also broken down into two, or split into two parts, which was
indicated and brake thermal efficiency.
Indicated and brake, good. Propulsive efficiency is a comparison of what?
Between useful power delivered from the change in kinetic energy of the gas.
Good, 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 good. And if you got an aircraft, what was better? If the speed is 400 miles per hour, which aircraft is better to use, a turboprop or a turbojet?
Turbofan. Turboprop, yeah.
Turboprop, yeah.
Turboprop, yeah.
Any propeller type aircraft, because large mass of air, small output, whereas jet engines are more efficient and don't like going slow. They like to go fast. Okay, so they're more efficient high speed. Good. Okay, that's fine. Well, I think we're about there for the moment. I'll save some more questions for later on. That'll cover those. So what we'll do, we'll continue a bit more. What time there? Yeah, that's plenty of time. We'll continue with repair. We'll finish off that bit. Let's get back to my page now. So good answers there. Keep it going. And we'll finish off on repair just before break time. Right. Let's get on to my PowerPoint. And there it is. There we go. Repair. All right. Where is he? We've lost one student. Where is he? First Manny. I've just seen 9 on the figure there. He's not in today at the moment. Hopefully he'll turn up at some point. Okay, right, let's get this started. Bear with me. There we go. Right, repair. Now, you'll have inspected your engine. Some parts you can repair in situ, but unfortunately you can't repair like things like turbines because that's within the engine. But the only thing you can repair really is probably compressor blades or fan blades, the front. Here's a quick question for you. What do you call a big fan connected to the compressor? What's another name for it? Who remembers that one? Way back last week. So a big fan attached compressor is also known as a, instead of a compressor, it's known as a, sounds like a big chicken.
Forgot.
What's another name for a male chicken? Or American one? Anybody? Well, that's one, but we don't call that the turbine or the compressor. An American slang name for a male chicken.
Turkey.
That's a turkey. That's not a chicken. That's just a big. Looks like a big chicken, a turkey. But that's a totally different bird. You might have heard this possibly. Americans used to call the big male chickens roosters. Yeah. So sounds like rooster. It's my way of trying to remember things. Different analogies. Some stick, some don't. Don't worry about it. So a fan attached to compressor is also known as, sounds like rooster.
Is it booster?
It is booster, good. So I call it the rooster booster. Yeah, just it's a daft way to remember it. But again, if it's silly, sometimes things like that stick in your head. If you anything that helps you remember something, do that with students as well. It's harder being online. When I'm in the classroom, I can show them the bits. I'll give you another example. The fuel-cooled oil cooler, right? What's the name of the little tubes inside the fuel-cooled oil cooler? I'll tell you an example of what I used to remember it. But what's the proper name? Has anybody seen any Keanu Reeves movies? Do you remember any films called The Matrix? Yeah, so when I'm pointing to actually FCOC, when I'm in the classroom back here, I'll say, right, that's the Keanu Reeves. And they go, what? The Keanu Reeves. And they go, oh, Matrix. So you go. So it's something that links to something, okay? Again, just a different analogy. So the little metal tubes are the Matrix. I call them the Keanu Reeves to help me remember they're called the Matrix, okay? So it's something relating to something. So if you can relate anything, whether it's to do with real time, anything to do with cars that might help you remember about an aircraft, then use it. There's no right or wrong way. At the end of the day, as long as it helps you remember the right name or the process or how to do something, then that's all it helps. Because at the end of the day, you just need to get the right answer on the exam. Okay, so there's weird and wonderful ways of remembering. Don't worry about it. I'll tell some more later on. Okay, right, back to where we were. Okay, right, fan blades. Yes, we can repair fan blades up to a certain amount. You'll be check them first in your visual inspection. Excuse me. So we're looking for dents, gallings, scores, corrosion, cracks, scratches, etc. There he is. There he is, past mommy. He's in. But there we go. He's back in there. Right. Yeah. So we're checking for all sorts of damage. And if you find damage, some is acceptable, especially on the back of the blade. The front of the blade is always quite smooth, but on the back of the blade, you'll get a lot of pitting. That's just standard. That's just the air tumbling around. It tends to cause a little bit of pitting. The severity of the pitting, though, again, you have to check for that. But as you see here, you've got dents, callings, scores, corrosion, pitting on the front. Not as you do get a little bit on the front, but not as maybe on the leading edge certainly, but not so much on the face. But on the rear face, yes, you would. Cracks, we don't like cracks. Scratches, well, that could be down to anything. It could be engineers, it could be something's gone down there. Again, all within limits. A burr, so scratch and raised bit, burns, damage repair already. Might be a bit blend, okay. So there might have been a blend. Wouldn't be that if that was a blend, that's a very bad blend. It should be smooth, so it should be nice and round. Now you would check all that. You would get a graph or it's an illustration of a blade, and it will tell you for that engine what limits you're allowed damage on and the type of damage and the repair limits within that. So you will be allowed to file blades. So for example, this one here, this one might be allowed to take or smooth it out using blends, using files to smooth it out. But again, before you go and repair any fan blades, if you find damage like that, you would go and look at the back of the turbine. And if you suspect anything's going down the engine, then borescope. But there's no point in going fixing 2-3 blades in the fan, which might take you an hour, maybe 3-4 hours, when there's damage inside the engine. So a small bit of damage on a blade might be fixable, but that might have gone inside the engine. So always check the rest of the engine first before you actually go and repair it. You will be taught how to repair blades. It's not as common now in the commercial aircraft because they tend to fly high and they very, very rarely get FOD damage. And if they do, it tends to break the engine anyway. The fighter aircraft we used to work on, we used to get quite a lot, just the nature of the aircraft and how they flew. And so we are constantly repairing blades. But yeah, check what's in limits. Cracks, we don't like cracks at all. If you find cracks, especially around here, that's an instant rejection. You wouldn't. Now, if you can change the blade, that's fine. Now, commercial aircraft, you can change the blade. Military aircraft, we can't. That's an engine out. But commercial aircraft, yes, you can replace a blade. But again, the books, the maintenance manuals would tell you exactly what's allowed, and that one as well. So you will have titanium. There were composite fan blades for a while, but composite fan blades, you're not allowed any repair. If you find any damage, that's too much stress. It needs to be replaced. Same for titanium. So the standard older steel ones, yes, you can file down, smooth down, and what you're doing is making it back into an airfoil type shape. Larger damage though, that'll tend to be, yeah, that's an engine out, okay, or actually replace the blade itself. But again, if it's that bad, there's a good chance the rest of the engine's probably been damaged as well. smooth it down. But I can see there that's a tear. I know for a fact any tears on the blade, then that's an instant rejection, just through experience. But again, you would follow your manual to the manufacturing instructions to determine what you can do. But because you can access that, and if it was in limits, and you've got to check as you measure the damage, and then you've got to allow for a certain amount of damage after that for you repairing it. And you've got to account that, will I be able to repair that once I take the damage out? Will it still be within limits? Okay, so it does take a bit of speciality. You don't get in there with a massive grinder and just go and grind it, because you're going to overstress it. But again, you will get a lot of training on that. Okay, now you can cut things out. You can use a disc, a slow rotating disc of a high-speed rotating disc of 2 inches in the air-driven motor. Okay, and you've got to have at least 0.06 inches or 65 metal must be left to finish off. So you can take a good chunk of that out with a 2-inch air disc, but you've got to leave about 0.6 or half a mil or so allowed just for hand finishing. Don't take it down with the air tool. Take the worst part out, and then as long as you're still within limits, you can finish off by hand filing the special file. We've got files called riffler files. They're very specialist files for doing contours, not just normal flat ones. And it's a specialist art. Okay, so take your time, and there's various methods of doing it as well. We've got things like crocus paper, very fine abrasive paper that will finish it off to a nice smooth surface. Anybody done or helped with any blade blending at all? Or seen it getting done? Not yet. It's one of those things you might come across it once in a blue moon. Certainly when in engine bay, we used to do engine blade repairs. They tend to leave it until it goes back to the engine bay, unless it's one that can be fitted in situ. If it's going to take too long, you're probably quicker replacing the blade. If it's a big one, it's going to take 2 or 3 hours. It probably is quicker. You can change a blade, within half an hour on some of the engines. Not a problem. Okay. Again, the back there, we can see. Well, this is going down an intake of different aircraft, and you can see the blades there. So again, access. If it's in situ, you have to squeeze down. If you're nice and small, it's great. If you're like me, a bit tall, but chubby, yeah, it's a bit of a tight squeeze, and it gets very hot down there. If you're hot country, down the aircraft intake, it's going to get not the most comfortable thing to do. And trust me, you've done that a few times. It does get very hot and sweaty down an intake. Big commercial aircraft, you've got a very obviously big intake at the front. You don't have to crawl down an intake on commercial aircraft, but certain military jets like this one, yeah, you have to crawl down a long intake before you get to the blade. So again, you've got to be careful. You've got things like FOD. Make sure there's nothing on your possession that can scratch certainly the intake here, or the fuselage intake, or it can be dropped out of your pockets. So make sure you've got no coins and any tools apart from what you're going to use. If you are going to blend the blade, you'd also do it about the 6 o'clock position. There's no point in doing it up at the top, because you're going to file and cut stuff. Well, the debris is going to fall down, potentially stick to another blade, and then get, if you don't clean it up properly. So always put it at the bottom, and put some masking tape down as well to catch the filings. And we tend to put it upside down, so the sticky part stays up. So any filings coming down, you can go into the masking tape, and make sure there's definitely nothing left once you finish the blend. And take it in shifts. If it's quite a big job, it's quite a major blend, then don't try and do the whole thing in one go. Go in there, especially if you have to crawl down an intake. It's not very comfortable. Give yourself a break, come back out, get some fresh air, go back down again, or swap over. Do it in shifts. You might have 2 of you doing it. One person, safety person at the intake, another person doing the job. Then you can hand over and give yourself a break. But again, luckily, on most of the jets you work on, you've got a nice big open intake, quite easy to get to. And remember, we said about the snubbers, the clappers, the midspan shrouds, they can overlap each other if there's been a surge or a stall, something like that. What did we call that name? What was the name given to a snubber going over another snubber?
It is start from yes.
Starts with an S, yeah. Sounds like jingled. Anybody? Remember when a tile...
That is shingling.
Shingling, yes, good, that's the one, shingling, yeah. So can we unshingle a shingle blade?
Hmm?
Can we unshingle a blade that's overlapped another one? Yeah, we can. Provided there's no more damage. If it's a case that's come over, it takes a lot of effort to do that. Yeah, remove it.
But for a short time.
For a short time only. Usually no more than about 20 hours maximum. I don't think it's got in the book now, but know the book will have it in 20 hours. Probably your older books there. It's certainly short periods only, provided there's no more damage to the blade. It's maybe just bent forward, fair enough. But again, that's going to be stress. If you imagine a blade has gone forward, there's going to be a lot of stress on the root because it's gone forward. All right, so again, that can cause a bit of problem. Okay. So most of the damage, again, for compressor blades will come from stone damage, or that's a nemesis or enemy. Bird damage, erosion, okay, things like that. If you see something like that, yeah, it could be a stone, it could be some sort of FOD, a bolt, or someone's hit it. Again, if one blade is damaged, there's probably another blade damage, that sort of damage there. That is potentially repairable. There might be a limit to about here, which we can actually cut that at a line called what's called cropping, depending on the size of the blade. Again, depends what the manufacturing instructions say. So yeah, stone damage, bird damage, erosion, and just unfortunately poor engineering. You know, leaving tools, leaving dirty marks, or stuff that shouldn't be there. So if you see something on the ground, put it up, put it in the bin. Don't leave it. Okay, so there we go. There's some other damage, compressor blades. You can just see, yeah, getting worse and worse to get back. And you can actually see here, they've lost all the rest of we've got maybe, I'm not sure that's the first stage, maybe second stage, third, fourth. Fourth is damaged quite badly. Then the fifth, sixth, and seventh, they've totally gone. Absolutely gone. Yeah. So again, foreign object damage is obviously we're trying to remove that where possible. And entity checks carried out on what? Yeah, if you're going to file a blade, like you've checked the engine, you're happy there's no more damage parts on the blade. What you would also do is NDT, doing your dye penetrant check first, because where the damage is, like that previous one, let's go back to it. Because yeah, you can see the damage, but there's a stress point there where the main impact was. There could be a tiny hairline crack which you can't see. So the best thing to do is do a dye penetrant NDT check. And once you're satisfied there's no cracks, then yes, if it is repairable, then repair it, because there's nothing worse. If you don't do that first, you go and file it, you get it nice and smooth, in with the limits, you go and NDT it, and there's a big crack there, a hairline crack. So NDT before, once you've finished it, NDT after, because even the stress of filing can induce a crack. So NDT before and after. All right, again, always follow the instructions, manufacturing instructions, what you need to do, and the limits associated with them. And I think if I've got, yeah, there we go. Some aircraft will have an air screen. Okay, now this is the same sort of material, the gauze you've got here, all right, and same here, especially this one, of what your protection guards would be on your standard engines. When you fit a guard to the intake, it's that sort of mesh that sits in there. But some of these are already fitted onto aircraft, especially helicopters. Okay, we want to try and protect them as best as possible. And you can see there, okay, there's the engine there. And you can see that there's an intake cover there as well. Okay, just to help protect from potential FOD. Because they've got big rotors spinning about, they can induce lots of dirt and debris, so they tend to have gauzes on them for the intakes. But certainly that mesh type there is typical of what you might see on an intake guard. All right. Okay. Never attempt to straighten out a rotor blade or vanes. Okay, so if you find a bit of damage like that, don't get your pliers and try and bend it back the way, because it'll probably snap. Once it's bent that way, it's bent. Never try and put it back to its straightened position. Okay, because you're stressed one way, so there's a good chance it'll probably snap off. So never do that. That needs fixed. Right, there's an example of in this illustration for give you repair limits and sort of depths and areas. Again, just a little example, the size of the blade, the areas. If you find damage in any areas, then certain areas, again, will allow 5/16 radius, 1/4 inch radius, whatever it is, for steel blades, for titanium blades, the type of it is. Most of the time, if you find cracks, especially cracks and tears, that's a big no-no. That's a blade replacement or engine out. Especially down the route, or if it's got a snubber or a clap in the middle. If you find a crack near a snubber, again, if that's a weak point, that's going to cause problems. So again, that would be rejection. So usually typical things like cracks and tears, that's a no-no. That's just you wouldn't even fix that. But the blade itself, you see these green zones, so it's telling you 5/32 depth, 1/8 of an inch of depth, you know, depending on the stages. 5/16 radius, so up area A here. Okay, you can put a little, if there's a bit of damage on the tip, you can round that off up to about 5/16 of a radius. Okay, and that's showing you how much you can take off in theory from each zone. And they've color coded here for a bit easy illustration. Again, we'll find all specific. The one in your book, I think the same one I've got already. It shows it slightly differently, but they are specific to each blade, and you just have to follow the information. Is it worth repairing, or is it going to be out of limits? The damage might be within limits, but you've got to think that once you actually repair it, you've got to go past the damage. So once you go past that, is that actually going to be out of limits by that point? You're just going to waste some time. But where possible, yeah, try and repair it. You know, again, follow the instructions, and if you've got the quality and the authority to do it, then certainly, if it is repairable, providing there's no more damage to the rest of the engine, then yeah, that's going to save some money. Okay, so that's what it's all about, saving the money, so you can get pay rises. Okay, that's just about it for the next bit. We are going to start on gas pass cleaning after tea break, and we shall progress on there. Okay, any questions before we go for a break? Oh, good. I thought somebody was going to say good night there.
Later on.
Right, okay, we'll see you in about 20 minutes, guys.
म यहाँ बसासँग निराइरहेको छु यार पुरै निन्द्रा लाएर तिमी अफिसै हो क्या हो
होइन घर हो म
ए आज हिजो चेक सक्यो होइन
हो
ए तिमीलाई पनि फ्री टाइम रहेछ अहिले त
फ्री टाइम छ
अब कहिले देखेर बिदा बस्छु कि बस्दैनौ
बस्ने एक्जाम
कहिले
एक्जाम अगाडि 4-5 दिन अगाडि 2 दिन जति बस्छु अगाडि
Again.
ल
Here we go again, getting there. So 2 reasons we carry out is to remove the dirt, obviously, from the engine itself, which will embed itself onto compressor fans. If you've got dirty fans, just think of a wing on an aircraft. If it's covered in dirt, then it's going to disrupt the airflow. If it disrupts the airflow, it's going to lift. Well, a blade on a compressor, if it's dirty, it's disrupting the airflow. Turbulent air, we don't like turbulent air down an engine, like smooth, directed air at correct time. Okay, so any disruption can possibly cause a stall. We don't want that. So it restores the engine performance, and to a certain degree anyway. It won't restore it 100%, but certainly will help. But the requirement is therefore to remove the dirt from the compressor. We can also clean the turbine a different way as well. But again, we're going to look at the processes, what's involved, how we do it, and a few other bits and pieces. So we tend to call this what's called a compressor wash. So say that could be you guys some lucky time doing that way up there, getting a good wash down the engine. We can also say wash the turbines, but it's normally only carried out on small turboprop and turbo shaft engines. Big engines like this is usually just a compressor wash. Okay, so we'll look at a few methods of how we do that. So in there you can see, not the best photograph, but obviously very dirty blades. So again, a lot of grubby, oily bits in there, which will attract dirt through time. They do get dirty, and they do need to be cleaned. So we can hopefully sort that out. Types of cleaning we'll look at internally and externally cleaning. External cleaning is covered under storage of gas turbines. We'll look at that later on. So we'll look at that at the end of this book. But again, we can use internal cleaning using dry abrasive grip process, or indeed a liquid wash. And we can use it doing what's called the dry motoring cycle. So remember, a motoring cycle is when we turn the engine over, usually with a starter, but without fuel and without ignition. Okay, we're just turning the engine over to get the revolutions. So it will only be a certain speed, okay, low RPM. If I'm doing a turbine wash, again, carried out doing a dry motoring cycle only, and always carried out after compressor wash. Okay, so we don't do a turbine wash until we've done a compressor wash. Okay, so we can just put it in now, I think. Okay, so we'll look at different names, different terminologies, the methods, the processes, and that sort of thing as well. So we're going to look at the abrasive grip process first. Now, it's not a case of getting sandpaper down there. We don't get too daft on it. But what we use is an abrasive grit. Now, we say abrasive grit, we class it as a vigorous process. So it's quite a rough process. And what we use food. We use ground walnut shells or apricot stones. They're ground down, and because they're hard, but they're not hard enough to damage the metal, because obviously the metal's hard on this. But if we put it down at a small RPM, and we throw it down there, as it goes round, it gently mixes together, and it actually buffs up all the material on the blades. It helps get rid of any debris that's on there. And because it's soft, injected into the intake engine, running at a specific power speed, and grit usually referred to, so this ground walnut shells or apricot stones, normally known as turco or carboblast. There are a few other names, but that's the most common names. So turco or carboblast. All right. So that's a typical sort of grit we're going to use. That's the names you remember. It's a vigorous process, ground walnut shells, apricot stones, turco or carboblast. Okay. Compressor wash, a bit more in depth. Again, classed as a liquid washing. You can see here's an example of a spray ring, okay, set up to the intake. All right, and that's going to direct a certain fluid into wash the actual engine itself. And most often, it's the most common method we've got. It will clean the turbine to a certain extent when you're doing compressor wash, but it's better suited than grit for that purpose. Again, if you put grit down a compressor, that's fine. Most of it get blown down and outside the bypass. Some of that grit will go into a combustion and possibly nozzle guide vanes, etc. But again, because it's basically a food, it will burn out if we do a running wash, a running process. So that's why they use the apricot stones and the walnut shells. because we've got, it says we've got small engines develop high power at higher RPMs, torque is increased by use of reduction gears. Again, if the engine power degrades, then that's going to be magnified by the reduction gears as well. So a slight drop in the power will be magnified by the reduction gear. So therefore, we can use quite a lot of thrust in propeller. So very important to make sure compressor turbine, small engines are always kept as clean as possible. Now initially, you might just get in the intake and just hand wash the compressor. But again, you can only get the fan, you can't really get back to the first, the second, third stages, etc. But even just initial clean with a solvent and actually get in there with your hand can help as well, because that's the main, we get main thrust from. Okay. Large and cleaning throat, yeah, you have a special rig. And again, you're just dry cranking over there. So you'll be spinning the engine on the starter motor. It's typically a larger one. You can see it coming at the back end there. Again, things to watch out for. Make sure there's nobody behind you. Okay, don't want to cover them in all the good old solution. Or equipment, you don't want to cover equipment because you're getting that dirty mix of liquid coming out. Do it in a suitable area. You can see there's a big door there. You don't want somebody coming out the door and getting covered in stuff. Large engines, so we cleaned in various methods. Sometimes there's actually what's called aircraft washes, where we've got it here in Scotland, where the aircraft will land because we fly over a salty air type environment. They will land as they taxi through. There's a big, massive, like a car wash. The aircraft taxis through and it sprays this cleaning fluid. Now that cleans the external part of the fuselage, and also some of that goes in the intake, and that gives a little wash to the engine as well. That's quite a common one for the bigger aircraft, not the smaller ones, but certainly the bigger aircraft. So yeah, prior to clean engine, it should be noted that use of methanol is also, so put this in your books, methanol, if you're going to use it for cleaning certain compartments, is very corrosive to titanium parts. We do use methanol for cleaning a lot of stuff, but be careful that if you're using it near titanium, you wipe it off as quick as possible. So not using engines that have titanium parts, obviously if it goes inside, that's going to corrode it, we'd have to wash it again. Engines that have been exposed to dry powder extension, again, that's titanium and all that good stuff. Usually temperature limitations for both internal and external. It might be possible to wash an engine internally until the EGT has dropped below a certain temperature, roughly 60 odd degrees. And you might need an ambient temperature higher than -10, because if you put a liquid down there, it's mostly water, well, it's just going to freeze, so it's just no point there. Again, let the engine cool down before you do any sort of wash, because you've got a chance of thermal shock. Putting a liquid down there, it's quite cold compared to the temperature of the core engine. So again, you don't want to cause thermal shock. And icing, again, if it's really, really cold. So we'll look at a few methods coming up now. For example, again, Paul, it's a bit small here, it's just an example. You've got a washing probe, washing tank. This is what's in your books. You can read through it. Again, it's just an example of what's going on, so we won't be examined on it. Wash probe, we've got a tank of 6 gallons, pump given output of 140 gallons an hour at 40 psi. Solution, 1 part cleaning fluid, 50 parts, and what we use is demineralized water. Okay, so there's no contaminants in there, so it's demineralized. You speak later on, you can use normal drinking fluid, but again, where possible, use demineralized or distilled water. So it's pure water. And you have a bit of kerosene, but it's fuel. So you're actually using fuel in there, some sort of kerosene, but mixed with the cleaning fluid. And what they'll say is you'll disconnect your P2, P3 air tubes, deactivate ignition system, which is obviously quite important, you don't get zapped. Fully open your VIGVs and lock in position. So you actually open to the minimum position like you asked this morning. So you allow the full flow to go in. Put your probe into the appropriate port. Carry out a 30-second motoring cycle. So start the engine as in run, but you've got ignition and fuel switched off. You know HP throttle. You have ignition on. You just got the starter going. After about 10 seconds, you pump the fluid for the remaining 20 seconds. Now, say 30 seconds because most normal starting cycles only last for 30 seconds. The circuit will automatically, or normally, automatically cut out at 30 seconds. You can bypass that if required. Again, if you're turning an engine over on the starter only, It depends on the type of starter. Certainly electrical starter, you're going to heat it up quite hard. If it's an air starter, that's slightly different. Okay, but you're still going to heat up the starter itself. So hence we tend to do only 30 seconds. Leave an engine to start for 15 minutes. That lets it drain away. And repeat 1 to 7, the stages 1 to 7, 2 more times. Inject 3 gallons each time. Again, you're not expected to remember this for an exam. This is giving an example of how we go through it. And then finally, let it drain for 30 minutes. Remove the probe, refit the blanks, refit your P2, your P3 connectors, and release the VIGVs and reactivate ignition. Always make sure it's fully dried out first before you put ignition back on. Okay. Start your engine, idle for 1 minute, and that will help dry the engine out and it'll stabilize. Again, you'll be watching all the gauges to make sure everything's where it should be. And then slowly increase and run for 3 minutes to dry out the engine. Don't go up to maximum too quick because you probably get a flame out. Increase speed slowly to maximum, so nice incremental speed. Again, allow it to stabilize for 2 minutes at maximum. Check for surge and stall. And if engine surges, repeat the wash. All right, performance check. So yeah, you've done a performance check before. You've noticed the performance was down. You'll have gone through all these steps here. Once you're happy the engine's dry and working properly, then you'll do your standard performance check again. And then fingers crossed, hopefully, your performance has increased, in which it should do. It can't go any worse. If it has got worse, you've done some damage to the engine. But normally it does increase a few percent or so. Okay. So watch out for things like exhaust flaming, not unusual in startup, following a wash. Flaming, again, get a big puff of smoke at the back end and actually just conking out. It also says engines will recommend a wash with water only for EGT recovery and use of cleaning agent only if there's been organic things like debris, bird strike remains. Now, if an engine has been contaminated by a bird strike, normally bigger bypass engine might get away with it, but if a bird's going down the core engine, that's usually an engine rejection. When unfortunately when birds go down it, they make a very, very big mess. And we've had a few engines on our engines, and there's nothing you do but bring the engine in, strip it down, and replace the parts. Oil deposits, in your case, usually possible you can remove with isopropyl alcohol. That's not that's not a sort you can drink. As an antifreeze, it should be possible. Do not use water flows greater than those recommended. Use of hot water and clean agents will also be more effective than use of cold water. Right. So again, be careful, although you're not starting the engine when you're doing the motoring wash, it is motoring over. So again, safety first, limitations, make sure you're doing a safe environment. Here's an example of a wash ring fitted on to an assembly, some sort of flexible hose which will spray the water out. There you can see them like guide vanes. Okay, and certainly you have the guide vanes and the VIGVs, they'll be straight. And some sort of tear ramp holding them. Okay, and then hand locked in position, and then you can actually sort it out. Large engine can require personnel to stand at least 1 metre or more away from intake while spraying. Again, 1 metre as well. You're spinning the engine over for safety. Water cleaning agents in the gas path. High bypass engines, fan is to be cleaned at the same time, so you clean this by hand as the engine gas path is cleaned. Again, so you do that separately. You probably clean those first and then do the wash ring next. Each blade should be cleaned at the 6 o'clock position. That prevents cleaner entering the bearing chamber. So likewise, if you're washing the fan itself, rotate it down like you do in repair, wash the blade by hand, spin it to the next blade, spin it, dry it, spin it, and so on and so on and so on. That stops any water process going into the bearing compartment. Again, it's different when it's motoring because it's going through with the airflow, so it should be bypassing the bearings. Wipe them clean, dry them off, and again, any solutions on the bottom intake, again, all clean up. You can use MEK and a fine Scotch-Brite material as required. Again, and any other parts like OGVs, outlet guide vanes, accusative panels, make sure they're out of the way. So you can do an extended dry motorcycle in the larger engines, so you can actually bypass it. Again, you've got to be careful with the starter limitations. So Small engine cleaner, this is a different version of it. Getting stuck in there. Okay, so a helicopter, obviously. Getting a bit of a clean it into the intake. That's a bit of a classic one there. Okay, good job. These actually soaked. So small engine cleaning, yeah, turboprops, turbo shaft engines. Again, the clean solution required will vary depending on the ambient conditions, as we saw already, and depending on the nature of the environment, if it's dusty or very cold, or etc. Types of deposits, desalination washes to remove salt and that sort of thing. Sometimes the salt that can be baked on over a period of time. And again, that will cause disruption of the airflow, which will cause disruption on your performance. So small handheld rigs, that could be a typical handheld wash on, basically like a power wash jet. And then you'll have your solutions, your cleaning agent, and your water solution appropriate to the mix, and that'll be sorted out. So small engine cleaning, compressor section wash, accomplished by injecting the appropriate fluid into the engine intake using either an installed compressor wash ring or simply a good old handheld one. All right. Turbine section wash, again done by injecting applicable fluid through a wash tube installed into a gas igniter. So you actually take the igniter out, and obviously because in the combustion section, you'll put the turbine wash appliance in there. And so when you spin the engine over, that will then go to the turbine. Fuel waste, 3 distinct cleaning methods are as follows. First one, compressor desalination wash, we just mentioned there. Pretty much used to remove the salt deposits, especially in this sort of environment. We'll be flying above the North Sea here, very salty air environment. But again, like deposits may also be removed. Wash medium that you use is drinking water, provided minimum standards are met. So you might have to filter it first, but you can use drinking water, but prefer to be demineralized where possible. Second one is a turbine desalination wash. Again, used to remove the salt deposits from compressor turbine blades. Wash medium, again, same as compressor wash, but also strongly recommended that the procedure is carried out when operating a salt-laden atmosphere. In other words, welcome to Scotland. Third one, compressor performance recovery washes. Again, uses approved chemical additives to remove stubborn deposits which cannot be removed during normal desalination washes. A bit more rarer, you might not come across that as much. It'll be the standard washes you'll probably get involved with. It all depends on the climate environment you're working on. For Nepal, it can be a bit dusty on the airport, so yeah, you might get debris sticking to the blades. Again, so maybe more intense wash. But again, you do that as many times as required. That method should only be carried out when engine performance loss is noticeable or trend monitoring dictates it. Well, you could say that for all three, because reason doing a wash, they might tell to do it at a certain airframe hours anyway. That's part of the procedure, just part of normal maintenance. Right, that aircraft, it's done 1,000 hours, it needs to have or the engine's done 1,000 hours, it needs to have an aircraft, an engine wash. Okay. Again, if you are finding a loss in power, a gradual decrease in power, then yes, a performance recovery wash would be definitely more involved. Again, your books, examples of wash schedules. Okay, various bits and bobs. Depends on the operating environment. Oops. The nature of the wash, recommended frequency, method, and remarks. So, like example, if it's continuously salt laden, desalination compressor turbine wash, daily motoring cycle, strongly recommended after the last flight of the day. Occasionally salt laden, so not as bad. Again, desalination wash, your weekly motoring cycle, strongly recommended. Adjust washing frequency to suit engine condition. Any type environment, performance wash. Let's give you an example of 100 to 200 hours, motor or running, because you can inject it when running, but again, you wouldn't have the same pressure of the rig going in, it'd be a slower pressure. Motoring wash for light soiling and multi-motoring or running wash for heavily dirty engines. And the note at the bottom says multiple motoring washes should be performed to the extent permitted by starter operating limitations and observe starter cooling temperatures. So I think we had examples in the book. Let's see where it was. It tells you, I'll just get the book around here. It gives you some tables. It tells you solution mixes and all that sort of thing. Again, any tables, you won't be examined on any tables, but some notes you might look at. You will have a look at a motoring wash. You will notice that the percentage is about 10 to 25% gas speed, and a pressure of somewhere between 30 and 50 psi, because you're motoring it, but you're not running the engine. So you need a bit more pressure for the fluid to go in there. So roughly about 30, 40, maybe 50 psi. A running wash, well, the engine's running this time, so you don't need as much pressure behind, because that could cause too much problems. So a running wash is around about 17 psi plus or minus 1. So with the engine running, you need less pressure for the fluid to go in, because the engine will pretty much suck that fluid in. So if you have to put that fluid in at too high pressure, that could possibly cause the engine to flame out. So when you're motoring wash, no ignition, no fuel, but high pressure to get the fluid in there. But when the engine is running, you need less pressure, and that compensates because the engine is already running. And some of the tables in your book, it will show you the mixtures by volume. And I think the only main note you should worry about is use of drinking water is permissible for motoring. Again, however, demineralized water is far preferable, but you can use standard drinking water if you don't have any, but always try and use the appropriate stuff. And then we've got various other tables in the book. There's a caution there. It says if you add 150 milliliters of what's called Witkonnet emulsifying agent and agitate the mixture thoroughly before use. So when you put your mixture in, make sure you mix it up properly. Don't just put it in, because it might not agitate properly. Okay, so that's the examples there. There's a water pressure rig. Okay, so depending on the type of machine you've got will depend on how you actually set up the whole thing. This is an example of a typical washing rig. So when desalination washing is performed in conjunction with each other, it's also essential that the compressive wash is carried out first. So before you do a turbine wash, make sure you do a compressive wash as well. Washing during a motor cycle ensures that emulsion fluid remains in liquid form. Okay, so if you do a running cycle, it would go frothy. And obviously, I've mentioned already, use of drinking water you can use, but where possible, use the demineralized water, recommended for performance running. Okay, that was a brief one there. Any questions on that one, on gas path cleaning? I think we took a lot of stuff out of the old book because a lot of different percentages and mixtures, but they're all examples. And anything examples you should be questioning on, but a few common parts there you want to make use of. Yes, we can use drinking water, but ideally demineralized. Running washes, 17 plus minus 1 psi, where a motoring wash, higher pressure, and that sort of thing.
Excuse me, sir.
Yeah.
In the dry motoring, we will not throw the fuel, yeah?
Yeah, dry motoring is you're only using the starter motor to spin the engine. There's no fuel, no ignition.
No ignition.
No ignition, no fuel. Yeah. Just purely, you're just spinning the engine over with the starter motor, depending on what starter motor you've got, obviously. And yeah, you're just rotating the engine on the starter. You don't open the throttle, you don't have ignition on, and you actually, to be honest, you would probably disconnect the ignition system. I think the old books you've got were a bit more in depth on it, but we didn't need to go that deep into it. But just be aware of it. Make sure at the end of any wash you do, make sure the engine is fully dried out, and certainly before you reconnect the igniter plugs, if you're doing a turbine wash, make sure everything is fully dried out. You don't want to be getting electrical shock if anything. Again, you do the funky chicken dance. Okay.
And then in wet motoring, we'll flow the fuel and start ignition. Everything we will do, yeah.
Yeah, once you've done a wash, you let it drain for about 15 minutes.
Okay.
Then you'll start the engine up, let it stabilize for about 2 minutes. Okay, that'll help dry it out once it's stabilized. And then slowly you'll take it up to maximum power, very slowly, because it'll still be a bit wet, a bit cool and that sort of thing. And once it's blown itself out, once you've got to maximum, let it stabilize, then happy days. And then once you're happy with all that, you then can do a performance check. Make sure the figures are where they should be. Again, if you found that the power has gone down before the wash, and you find the power is still down after a wash, even though you've checked internals, seems okay, it might be just a very, very tired, worn engine. It's time to come out. But you tend to find, unless it's been damaged, the engines will stay in up to a certain amount of time. Remember, the turbine is the least lived item, the smallest amount of hours on it, so the engine will only stay in for so long anyway. So usually engines will stay in until there's any damage. You know, they'll say they've got 1,000 hours of flying in them, they'll stay 1,000 hours unless they get damaged. Give them a clean every so often, yeah, that'll help keep them in tip-top condition. Okay. Other things to remember, yeah, make sure if you hand clean the fan blades, do it at 6 o'clock position, based at the bottom. Know the types of material used for the grit process. So your ground walnut, your almond stones, ground down, and it's classed as a vigorous, so a very rough process. Remember the names are the process is called Turco or Carboblast. And obviously, if you use a methanol, don't use it in any parts that have got titanium within the engine, which is most engines do have. Okay, so that's pretty much engine gas pack. We've actually condensed it now. The old book had a far more in depth on it, but it wasn't needing to be that in depth. As I say, if you remember those part ones, small engine cleaning tends to be for your turboprops, turbo shaft engines. Again, depends on the nature. Yeah, where would you do a turbo? How would you inject turbine wash, or how do you induce a turbine wash? What would you put the probe through? Or the equipment, where would you fit the equipment to do a turbine wash? Anybody? So the compressor wash is easy. You attach it to the outside of the fan and it goes down the compressor. But how do we get the probe to enter to wash the turbine section? Where would you fit the equipment to give us access to the turbine? Anybody? No. You would remember, speak about igniters. You would take the igniter out. You fit the tube into the igniter hole, screw it down there with the spray assembly, and that will spray into the igniter hole. So that will go in the combustion chamber and then get blown out through the turbine on a motoring cycle. Okay. Remember your internal cleaning and wash methods. You have 3 distinct types: your compressor desalination wash, your turbine desalination wash, and your compressor performance recovery wash. I mentioned already, motoring wash, usually around 10 to 25% RPM. Water cleaning mixture with a pressure of about 30 to 50 psi. Your running wash, where you're actually running the engine, you've started the engine up. Again, usually about 60% NG, so just about idle, to be honest. But a lower pressure rating of about 17 psi plus or minus 1, because you don't need as much pressure because the engine's running, so it can actually draw the fluid in. Okay, the drinking water mentioned already, and that is about it. Just want to see if there's anything else I can show you. A new one. No, tables, just examples. I mentioned the water. You can use drinking water, but ideally, what do you call it? Forgot myself now. Drinking water, but demineralized water. Sorry. Yeah. So again, if you are going to use drinking water, it depends on the countries around it. Some can be cleaner than others. So again, ideally, you want nice, clean, filtered water where possible. General equipment required for motoring wash or running wash. You have a wash cart like we showed you there. Steel containers, some sort of mechanical agitator or recycling pump with a relief valve. And we have 2 control valves, 2 air valves, 2 fluid shot valves, suitable tubing for connecting. Again, just an example. And then all you're going to do is follow the manual, follow the mixture requirements between the water and the solution. Okay, like we saw before. And then once that's happy, all is good. Engine motoring washers, again, compressor desalination wash procedure, depends on the ambient temperature, so watch out for that. Remember 30-50 psi. If you use a compressor wash rig, drinking water boosted by a centrifugal pump can be used. So centrifugal pump, which you use for air, you can also use it for fluid. And you see that, and you can go back to my cars, your water pump is a centrifugal pump. Wash ring, etc. And one of the big cautions is do not motor more than 30 seconds and always observe your starter cooling period. All right. Other warnings, if you're disconnecting igniters, residual voltage in ignition sector can be very high, obviously very dangerous. Ensure ignition has been switched off for, highlights in your book, for a minimum of 6 minutes. Okay, so make sure ignition has been switched off for a minimum of 6 minutes. Normally, if it's doing a spark plug, it's 1 minute for surface gap, 3 minutes for air gap, but the ignition system, just make sure it is disconnected for 6 minutes. Quite important on that one. Also says always disconnect coupling nuts at ignition exciter first and use insulated tools to remove the same. Do not touch output connectors or coupling nuts with bare hands. However, if you're going to do a motoring wash or disconnect the ignition first, what are you going to do first? Circuit breakers, power, weight, before you do it anyway. Okay, but if the engine has been wet in some variety, then you just never know. That procedure we've got on page 129. It will be something similar in the old book. Again, it's just an example of how to do it. I'm not going to go into that one. Only thing there, the last part says install igniter, new gasket, tighten igniter and torque to 300 pounds-inches. Slacken to 0 and retorque to 300, 360. That is an example because it will be more specific to the type of igniter you have. The other ones we've got is, no, that's the same. Running washes, as we mentioned already. And a big caution we've got on the last pages, we go from power implementation, is to limit possibility of engine over temperature or over speeding. Thoroughly agitate the solution. Make sure you get a good mix with a clean solution prior to during the wash. That prevents separation because maybe using kerosene in there. So you want to really agitate it up, make a good mix together, and not stop it. The use of that with condensate emulsifying agent, or technically the use of mechanical agitator or pump with refill, strongly recommended. Anything else on there? It says do not increase your speed above 60% or ground idle, whichever is lowest during a rinse cycle. When you do a rinse cycle, you just leave it idle. Just start it up, leave it idle, no more than that. Inject your rinse solution into the engine. Again, if potable water is not available or questionable, the post-rinse cycle may be waived, providing the cleaning agent used was specific to the type. As I said there, complete your rinse cycle, increase NG to 80% for 1 minute, ensure complete drying. Once you're happy, shut it down. Once you're happy, the engine's dried out, all indications are normal, let your engine cool down, a couple of minutes, and then shut it down. And then, if required, go and do your power checks. Okay, so that's pretty much it before we move on to power augmentation. Have a good time. Oh, bargain. Right. That's any questions on that at all? Keep to the basic ones I've just mentioned there, and you should be okay. We've actually reduced quite a lot there. Any questions? Okay.
Is there no any highlights and important for the exam, this type of this NG and others?
The important parts, the ones I've just mentioned, yeah. The ones I was highlighting, the types of grit, making use water, the methanol. Yeah, all those ones. I've just gone through. That's the sort of main ones you want to go. We'll go through it again, but that's the main ones I've highlighted in the book, and for you guys to sort of highlight in your books. I know you've still got the old books, haven't you? Yeah. I thought Sanjeev might have had them printed out for you by now. Yeah, because normally we'd follow the book and I'd tell you page this, page that, highlight this, highlight that. It's hard to do that when you've got the old books. Only thing I can suggest is Sanjeev, maybe I've given him all the new books as an online. He can maybe email them to you if you want. If you can't get them printed out in time. The old book is sort of the same, some parts are the same, but because we've moved it all about, It's not ideal for me going back, well, for you guys for going back and forward in old books. You should have had the new books. I don't know why they haven't printed them out for you. They were given to the company, so it's on that end, unfortunately. This part, we've condensed the grass path clearing. In the old books, is a bit more extended, but the main parts, I'll say, I'll highlight those bits, okay? But we'll recover this again this afternoon and definitely tomorrow anyway. The bits I've gone over there, that's pretty much the main parts you want to remember. Any module you do, it's got a table in it, bar very few. That's just for information. You cannot be examined or given a question on information in a table. Okay, that's not allowed. But any notes that we highlight, then yeah, they're probably worth noting or highlighting in your book. Okay, right. Let's go for a quick break again. Come back about 20 minutes, 25 to. And then we'll start on power augmentation just before lunch. And then we're not far left, not much left to do at all. Okay, so we're just about, yes, we get more air in, we can add more fuel, that'll get a bit more boost, but we need to re-establish it. So we'll do what's called a water and a methanol mixture. So the graph you got there is static thrust. We have temperature on the bottom, so from minus 30 up to about 50. Standard power thrust without injection, but by using a water injection, we extend that thrust line to a higher ambient temperature. So the dashed line here represents by adding water injection. So where it starts to drop off, around about what we've got there, about 18 degrees, 20 plus degrees, it starts to drop off the hotter it gets. But by adding water, we extend that line a little bit longer, which is always good. And the same for max shaft horsepower. You've got your takeoff power. Without water and methanol injection, yeah, it tends to peak off quite quickly for a turbo shaft. By putting water methanol in, whoosh, it restores it up to a high temperature. Yeah, so it's really good. Because remember, on a turbo shaft, you've got a standard rotor that'll keep the blade at pretty much a constant speed. So it's just a representation there of what you might actually come across. So compressor inlet injection, the two basic methods of injection the coolant into the airflow. Okay, so quite straightforward, this one. Straight enough, directly into the compressor itself. All right. So by putting it straight into the compressor, you're going to cool the airflow as it heats up. Because remember, an axial flow compressor, it rises temperature per stage. And what was the temperature rise per stage of an axial flow compressor? Do you remember that one?
Excuse me, what?
Remember said that every stage of compressor, an axial flow compressor, the temperature rises. So what was the temperature rise for an axial flow compressor?
1.1 is to 1.1 to 1.
Not the pressure rise, what's the temperature rise? But you're right, that's a...
yeah, 25%.
25 degrees, yeah, 25 degrees. So by cooling that, we can get more air in, yeah, because the expansion goes through each stage, it will expand, and pressure increases is great. But if we can get more air in, as it's doing that, that's fantastic. So what we do is we spray a water methanol mixture, not just water, but a water methanol. If you just put water on its own, yes, that will condense it and we get more air, but we also reduce the core temperature, the turbine inlet temperature. But by adding water methanol, the methanol acts as a fuel. So yes, the water methanol is quite cool, mixed with the water. It condenses the air, which is great. We can get more air in. But as it goes to the combustion section, well, that methanol is quite flammable, isn't it? So it will ignite. So it will re-establish the core temperature. Also, if you're putting water into a compressor, it's going very fast. There's potential it could freeze. So the methanol itself acts as a coolant. It acts as an antifreeze to prevent the water from freezing, and it also acts as a fuel to ignite in the combustion section to re-establish the core temperature. Because said, if you just put water in there, you're going to cool the core engine, so you're actually going to deviate from what you're trying to do in the first place. So the methanol does an important job, yeah. Coolant, antifreeze the water, and also acts as a fuel. All right, and so you get a good boost through the engine. All right, power is restored, and you don't have to adjust the fuel flow. You can keep your fuel flow as normal, but you've re-established the actual core temperature. And we can also spray it into the combustion chamber inlet, so we can directly into the compressor, or we can spray it into the combustion chamber, or a mixture of both. Okay. So 2 ways of getting it in there. So compressor inlet injection. Well, we need some sort of system to supply the mixture into the compressor. Now, if you look over here, before we look at all the gubbins here, there's your IGVs. Okay, so the fixed ones. There's a first stage compressor. You can just see the rotors there. And you can see, obviously, there's a function to supply from an aircraft tank, a separate tank that's full of coolant, to spray it into the rotor. Now, as the rotor's spinning, it's going to spray it out, and then that will go back to the compressor. Okay. So we're going to use HP oil, we're going to use spill oil, we're going to use torque meter oil, servo. We've got servo again. There's the water methanol mix, your atmospheric air, and purge air. So if you look here, we've got a big valve. Now, basically, this big valve here is going to go up and down at a certain time. Normally, it'll be kept push shut. Yeah, these dots here represent a spring. So the spring's going to keep this servo piston down, which is going to block off the supply of coolant until we require it. Okay, so we need to be able to push this piston up at a certain time. Now, in the cockpit, you'll have an HP oil cock control lever or a switch, depending on the system. Now, you can see there, it's basically on-off control. Yeah, at the moment, we've got oil pressure in there, or we can switch it off. So if he selects it on, we can use the oil pressure from the gearbox, because that'll be going quite fast. Well, if you get oil pressure, well, here we go again. We've got a servo valve again. Yeah, just like we saw back in the fuel system. Servo valve, if it opens, it's going to allow when you select the oil control lever here for selection of injection, it will allow the oil pressure to come up, open the servo valve, which will then flow into the underside of this piston, which will then push that piston up, open the valve here, and allow flow of the coolant to the rotor. Well, that's all very well, but we don't want to open at the wrong time. We don't want to open when we don't need it. So again, this will be restricted. And look, lo and behold, look what we've got again. We've got an aneroid capsule, an evacuated capsule, and also an atmospheric capsule. Again, just like we saw in the fuel system. So depending on the altitude, depending on the forward speed, these will be fighting against each other. Okay, so it will give a proportional control of the servo valve. All right, and you've also got the torque meter system. So you've got a torque meter system fighting against this. You've got the forward speed of the aircraft. You've got the altitude, all getting to a position which will determine how much that servo valve moves. Although the oil will move the valve, all this here will determine how much it allows that to move, which will determine how much that piston moves up to allow a proportional amount of fluid to the rotor, which will then provide the right amount of thrust. We don't want too much. We don't want it on the ground when it's a cold day, and you can select it anyway. But just for instance, you don't want it at certain occasions where it could overstress the engine. You need to supply the right amount of fluid under the right conditions. So altitude, forward speed, and torque meter pressure as well, all working together to allow this servo valve. Oops. So there you go. There's your atmospheric pressure. There's the servo valve. So again, this will open proportionally to whatever is going on within these two capsules and the torque meter system as well. Okay. And with the oil pressure from the actual engine, the RPM speed will also determine how far this servo valve is allowed to open. Okay. And that's basically what's happening. All right. Anything else I want to put on to that one? No, that's the same. That's pretty much the basic setup. It looks more complicated than what it is, but I can't put my hand over it obviously, but if you to cover this part up here and just show you this valve, spring pressure, you've got a maximum stop. Under spring pressure, now you can see here, you can actually set that pressure, so increase or decrease, again, if it's wearing out or whatever. So you've got oil pressure, which is normally closed off initially. The green is a spill oil, because you will have spill oil from servo pressure, again, just like the fuel system. So the servo pressure increases, the delivery output will also increase. But likewise, servo pressure initially will be helping to push down on the valve, assisting with the spring. But when we open the valve there, servo pressure will decrease in this case, which will take the pressure off here and allow the piston to move up due to the higher pressure from the HP inlet. Okay. And then depending on what position the vacuum capsule and the atmospheric capsule are in, and also the torque pressure one is in, will determine the position of these needles. And again, you've got springs here controlling these two types of needles. All right. So the more these are moved out there, the more pressure in here, okay, the more that will determine the movement of this whole assembly here. All right. And you can also see here we've got some purge air, we've got some compressor air. So when this valve is shut, we don't want it. We don't want this fluid left in here. Okay, so we'll get a small tapping when the switch is section off that will actually purge the fuel, not fuel, sorry, the water methanol mixture in here, because the water sat there, well, water's corrosive, so we can actually use a little purge of air that will blow whatever else is out in that line, provided this isn't activated. Obviously, it helps blow it out as well. Okay, that helps to purge the line. Okay, so that's the basic of compressor inlet injection. Okay, well, we'll recap it a few times. And the ring where the fluid goes, we call it the flinger ring because it flings it out. That's the proper Scottish terminology, that one, flinger. Okay, so it'll fling it out to the rotor blades will spin it out, and it will go back through the compressor. So that's a basic setup for compressor inlet injection. It looks more complicated than what it is. All right, so there's your valve, which will move up and down accordingly. Okay, so at takeoff, revs, minimum ISA sea level conditions. If you open that oil HP cock, oil will force open the shuttle valve, like mentioned already. Supply servo pressure to push the servo piston and open the metering valve, as you saw already. Forces on the capsule stem are rated so that specified torque meter pressure is required. Again, this is recorded in the engine logbook to bring the control assembly into balance. So if I just go back quickly, so you torque meter pressure, that will be set and adjusted. So even though you've opened the HP cock, it will be reacting against the pressure on this needle valve. Yeah. So that's set pressure, which can increase or decrease accordingly. We don't want to open too quick because that could probably put too much pressure on the engine. Temperatures above ISA and at altitude, the top pressure decrease will be greater than ice conditions and the sea level, and the resultant imbalance force on the capsule stem allows the shuttle valve to open and increase the servo pressure. Now, more oil to go towards the piston. Balance control assembly is reached when increased water methanol flow has restored the standard altitude top meter pressure. So once we've got the top pressure back up, that will push that valve back down, which will stop the servo or reduce the servo valve, which will decrease the amount of oil going to the piston, and the spring pressure will take over and push the valve, the big valve, back down again. Mentioned about purge air. So to prevent corrosion, because you've got water, methanol's okay, but again, we don't want water methanol sat there. So to prevent corrosion, supply of air tapped from engine, fed to the metering valve chamber to purge all residual water methanol from the control unit and from supply passages in the engine impeller. We don't want it sat there, okay? So that's your compressor injection system. Again, for the moment, we'll just go through it at the moment. We'll go into the combustion chamber one, and then we'll recap these after lunch. So combustion chamber injection, similar sort of setup. Again, instead of injecting compressor, we're injecting it straight into the combustion chamber. Now, what you'll find is, if you look down this picture first here, we have got a burner. Now, just for a bonus point, before we go into injection system, can anybody identify what type of fuel burner this is?
Atomizer.
Atomizer? And what type of atomizer is it? I'm pointing at these two parts here.
Not a hockey stick.
Yeah, it's not a hockey stick, because that'd be a vaporizer. So think of the types of atomizer we have. Look at
Simple and duplex. So it must be duplex, yeah.
Yeah.
Because
Now,
it has two holes, yeah.
Yeah. Looking, I don't know if you make out the size on your screens, it's maybe a bit hard to see, but there's two different sizes here. Which one's the primary feed? Which one's the main feed? The left one or the right one? Which one's primary?
The one which is smaller is a primary.
That one there?
Yeah.
Yeah, that's the primary. And then your main one, which
is big, is a secondary.
Good, good, good. A bit of recap, okay? Throw some random questions in there. Keep you on your toes. All right, okay, right. So we've got a basic diagram. You've got LP water, you've got HP water, cooling water, HP air, and we've got oil. There's no tank. Okay, we've got a turbine pump, we've got water, and that sort of thing. So basically, all the system, when we select it on, switch it on, it's going to allow water methanol. Now, this burner will have a special connection to it. It's got a separate hole that goes down to the bottom of the burner. So it sprays it directly into the combustion chamber, which will again go through the swirl chambers as well, mix with the fuel, woof, bang, especially the water methanol in there. So at high ambient temperatures, airfield is above sea level, engine produces less thrust, like we saw before, which reduces the mass flow. So an increase in thrust above normal, obtainable. Such conditions can be achieved by running the engine at higher RPM and so on. So operation, the water is delivered by a turbine, which is obviously there. Now, what type of turbine do you think that would be? Would that be an impulse or an impulse reaction? Smiley face or Nike tick?
It looks like a smiley face.
Yeah, we don't need the velocity of air over it. We just want direct impingement. So yeah, we'll have an air inlet. Okay, I'm going to spin it, go on selection. That will draw the water in. Okay, and then we can have a supply of the fluid going out and so on into the actual component. All right. So water. Yeah, the water methanol. Yeah, the water methanol itself. So same fluid.
Water methanol is ejected into a primary or the secondary?
No, it's separate. It's actually in between. This is a special connection on the burner. There might be some of the burners. Maybe half the burners will have this system in it. Okay, it might be one burner. So it's only the burner will have. Though you get primary and secondary feeds, this actual feed is in between. See, it comes out the bottom here. So it's got its own bottom. Yeah, right at the bottom. Yeah. There would be your primary and main feeds as normal, but on this burner, it's got a separate drilling. Okay, so there's actually a hole in between the primary and main feeds. Okay, purely for water injection. So it's got three.
It is ejected just before the primary.
Yeah, yeah. It basically comes out of the bottom of the burner and then also gets blown through the swirl chambers and mixes with the fuel that's already there. So it combines with the fuel as it goes in the combustion chamber, and also with the methanol in there, that will ignite with the fuel as well and help restore the. Because remember, you've got cooler air coming in from maybe compressor injection. But if you do direct injection, it already ignites, which is good. Okay, so this burner, although it's got its primary and main feed, it also has a separate drilling through the middle of the burner itself with a very small water jet out the bottom. Okay. So just a slight modification to the normal burner. All right. Okay. So yeah, operation and pump control by shutoff valve. Air supply again. A warning light tells the pilot that the valve is open. We need to know that the valve is open. If it opens up uncommanded, we don't want that because it might give us too much power at the wrong time. Valve is open and water is being delivered to the engine. Water pressure operates a reset on the fuel regulator. We've got need to actually regulate the fuel. Provides required increase in fuel flow to raise your RPM and your EGT. We have a water flow sensor. Again, provides a signal water flow and also ensures safety by preventing water flowing into a failed engine. We don't want that flowing into an engine is maybe flamed out, and the air and combustion temperatures, pressures from not entering the system when not in use. We don't want it going when it's not in use. So basic controls you'll have is a master switch common to all the engines and individual throttle operated switches for each engine. As we said there. So a turbine pump driven by air, tap from engine. So again, we use an air system to actually turn a turbine. Okay. Water into combustion chamber liners provides the cooling. And again, as I said there, a warning light, that's the main thing. We need to know when it's operating. So a warning light there will come on, let the pilot know it's activated, that the water has been delivered to the engine. As I said there, pressure operates a regulator, which then provides required increase in fuel flow to raise RPM. And the flowing sensor allows us to know the water is flowing and ensure it doesn't go when it shouldn't be going as well. So your basic control, as I said before, a master switch common to all engines and individual throttle operated switches for each engine. So you'll have a toggle switch will activate for each engine. Although it's common to all engines, you might have a problem with an engine. If it doesn't work, you can have another engine just in case one engine fails. All right. Okay. So again, it depends on aircraft type. So engine running, etc. Have it some sort of switch in there in your quadrant. Engine running, the master switch will be set to prime. That'll make a circuit and is made on the throttle micro switch. So opening throttle to take up position operates the micro switch. When you have the master switch set to prime, so that's preempting you're going to use the injection system. Increasing P3, which is HP delivery air, pressure opens the water shutoff valve, and at the same time activates a micro switch to complete the circuit to the air shutoff valve. Okay, in other words, it's going to allow shut off valve and allow air to go to the turbine. Air valve opens, air is fed to the water pump turbine, the impulse turbine, and indicating the light will now start flashing to give attention to the pilot that yes, it is working. So that indicates that air is now flowing. The P3 air accelerates the pump turbine and water will be delivered to the force sensing unit, opening the sensing valve, and then pass it via a water manifold to the spray nozzles in the combustion chamber. So the spray nozzles is your burner nozzles, yeah. Interaction, water injection can be terminated or switched off by moving the throttle back from the takeoff position, and that will break the micro switch at a predetermined level. We only need extra power at maximum. There's no point in having an injection system when at idle, because that doesn't make sense. No point halfway there or 80%. So we only need extra power when we're at full throttle. Yeah, so a little micro switch will disengage the system and switch it off as soon as you move your throttle back from maximum. The sensor valve when open operates a micro switch as well, so that causes the flashing light to remain in a steady on condition. Indicates the water is flowing, so when it's flashing, the air is flowing. When it's on, steady, that lets you know the water is flowing. Now, as a safety thing, I need to highlight this in red just to make sure. Unless water flows, make a note of this one in your books, guys. Unless water flows within 5 seconds, the time delay unit will automatically cancel the system. Because if it doesn't start flowing and you're tapping air off, you're going to decrease a bit of thrust, aren't you? If you're tapping air off, extra air off to power the turbine, and water's not flowing, then you're not going to get power. You don't get the extra boost. So you need to cancel that and try and use what power you've got already. Okay, so within 5 seconds, 5 seconds on runway, that's a long distance. All right, so very important to highlight there. So within 5 seconds, it will switch it off. And that also protects the pump from dry running. So we're not running the pump dry. Okay, any questions on that? Just double check on the slide there. It's come up a bit funny. I don't know what's happened to PowerPoint. My PowerPoint's gone all funny for some reason. Enjoying that. I have to look at a few bits, sort it out. Right, the bit I was trying to find there. Let's see what it's doing there. I'll just have a quick look. No, that's fine. It's just a bit of seam that for some reason still there. Okay. Everybody happy with that so far? But we'll recap it again. Don't worry, after lunchtime. See it's going there. So that is water injection, either in the compressor or compressor and the combustion chamber, or just combustion chamber its own. You can put water in its own, but water that causes problems with freezing. So the water methanol, the main thing to remember is the methanol acts as a coolant, so it helps cool the air. It acts as an antifreeze to stop the water freezing, but it also acts, the main thing, as a fuel to re-establish the core temperature of the engine. Okay, so it does a lot of things there. And that's about it for water methanol injection. When do we need it? High outside air temperatures, okay, where the engines need more oxygen, need more power, so we can condense that air, okay, or actually increase the core temperature of the combustion chamber, give it more next to bang. We don't use nitros, okay, like Fast and the Furious, but again, going back to cars, that's how they get more power, by putting that very, very, very cold nitros into the intake. That cools the air down. Okay, they can put more fuel in, more fuel, more air, more bang. So that's what nitrous does in your car, providing your engine can handle it. Don't just put it on any car. All right, so there we go. There's that. Last part we've got is after burning or reheat. Afterburner is Americanism. Reheat is what we call here in Europe and UK. And all we do, simply do, is we add fuel into the exhaust. Okay, and the one thing to remember from this one is it doesn't affect the main engine, doesn't affect the core engine as such. Okay, so let's have a look at that. The reason we've got this in the section is at the moment EASA still require, because the possibility this good old jet is going to come back into service. It's never going to come back in service, but at the moment we still have to teach reheat and afterburning. Only time you'll work on reheat system is if you join the military. So if you want to do that, go and join the military, you'll work on reheat system. There are some civilian companies design a transonic jet which does have reheat. So yeah, maybe in the next decade or so there might be a new version of that one, possibly. But again, probably not very unlikely. So it's usually a military option. And in fact, the engines for this old Concorde aircraft, which is the fastest aircraft in history, for a commercial one anyway, it actually fitted the engines from what I used to work on, Tornado engines, initially as a trial. Then they fit the Olympus engines. Amazing bits of kit. Very fast aircraft, very noisy. All right, other versions got the little Lightning again. That jet there was basically a rocket with a pilot attached to it. That used to be the fastest jet in Britain back in the 60s and 70s. It didn't fly very long because it used a lot of fuel. A twin engine set up like that, and you can see the reheat coming out the back end there. All right, but it was generally a multi version. So basically, what do? We add exhaust onto the exhaust, or within part of the exhaust, we'll add some more fuel spray nozzles. Okay, we add some extra burners. Now, there's no ignition for this. We don't need an igniter because you've got the hot gas coming out your standard engine, and by the heat of the gas come out, which is what, 600 degrees C, that sort of thing. If we spray a fine mist of fuel into this hot gas, it ignites straight away. So you don't need an ignition source. It's purely the heat from the gas that will burn. Now, as the gas comes out the normal engine here, you also have a little bit of fuel. You also have a little bit of oxygen left in the gas flow. So again, mixing with some extra fuel gives us more bang as well. And it will reburn any unburnt gases. So the nozzle at the end of this, to accommodate this extra pressure, because we're going to expand more volume, we have to have, instead of a fixed nozzle on the normal exhaust, we have to have a variable nozzle. So the nozzle needs to be able to move to accommodate the extra volume and maintain that back pressure. Okay. So what happens is, if you go for selection of reheat, we'll be at maximum thrust. All right. Then we'll go through a gate, positive selection into reheat. And you can have minimum reheat and max reheat, so a little selection after there. And the main thing to remember from this is the nozzle at the back, okay, even on selection reheat, the nozzle has to open before the fuel goes. because if the fuel goes in first and ignites and the nozzle doesn't move, we can get a back pressure through the engine. So the nozzle must move first. So what we call it is nozzle, fuel follows nozzle. So the fuel will follow once the nozzle has opened on selection of reheat. After reheat examples, an engine with a specific fuel capacity of 1.15 at sea level and at speed of Mach 0.9 initiates 70% reheat under the same conditions of flight. Consumption will be increased from 1.15 to 2.53, almost double the amount. So we actually use double the amount of fuel, and we almost double the amount of heat as well. Increasing altitude to about 35,000 feet will also bring specific fuel capacity down about 2.34. So in other words, we can get more oomph, we can get higher quicker, and then we can bring the fuel level down once we get too high. You don't need as much power. Specific fuel consumption measured in pounds of fuel burnt per hour, okay, or pounds of thrust produced, and is normally shown as a figure with no units. Hence why we've got the 2.53 and 115, yeah? So there's no units there, it's just a figure. So that's an example. The degree of extra thrust obtained is wholly temperature dependent. An example I've got there is gas into the jet pipe will do so at a velocity of around about 720 feet a second to about 1200 feet a second, and the requirement is to accelerate at higher velocities. In older spool engines, there was little gain by reheat gases. There wasn't too much. You used to actually attach rockets to them, and you get roughly about an increase of 7% to 10% static thrust. But nowadays, okay, there's an example there. Assuming example jet pipe temperature is 650 degrees and a post-afterburning temperature of 1500 degrees, so double the amount, then temperature ratio will be 1.7. And again, just little examples, don't worry too much about it. The square root gives you 1.3. Jet velocity has increased by about 30%, ratio of about 1.3 to 1. You won't have to calculate an exam, so don't worry. Overall, what you want to remember though is reheat or afterburning can give you 80% more thrust. Okay, but also your fuel consumption goes through the roof as well. All right, so it can give you 80% more thrust. All right, so to make sure maintain the pressure, as I said before, we've got to have this nozzle has got to move back and forward. It's got to be twitching the nozzles. You might get a couple of different types, and the two types we're going to look at are these interlocking feather type ones. We used to call them petals where I worked from, but we call them turkey feathers. So the turkey feathers, appropriate for Christmas. Turkey feathers, or we have movable eyelids. All right, so these eyelids, just like it sounds, they be open and close, almost like the clamshells for thrust reverse. The same sort of thing, and all this is doing this time is allowing the pressure to maintain constant within the jet pipe assembly. If we don't do that, then the pressure will build up too much, and we'll go back through the front of the engine and stall the engine. So the main thing about reheat is it should not affect the core engine. The core engine will still work as normal, even at maximum. All we're doing is add an extra bit of fuel in there, having a bit extra more heat, a bit more velocity coming out, but it doesn't affect the core engine. Okay. Anything else? So yeah, that's your two. So the two types, interlocking spokes, turkey feathers, there's a common name for them, or the eyelid version. The eyelid version was the type, I think it was on the Concorde aircraft we just saw. The turkey spoke ones, again, the type that was used on the Tornadoes I used to work on. I might try and find a video for you. And there's the basic selection. You have the pilot's lever, your throttle lever, your cutoff normal range, and then at maximum, and then there'll be a point where you push it through from maximum, you'll feel a positive selection. That'll be minimum reheat, and you push up to maximum reheat. In the case of military aircraft, we had a range called combat. That was basically the engine on self-destruction. That was get the aircraft out as quick as possible. It's getting chased by a missile. Again, you don't have that in commercial aircraft, thankfully. So when you open the pilot will operate the nozzle area or the fuel flow, pilot selects reheat. There'll be a pressure sensor cost. Now the good ones to remember here is P3 is your compressor delivery and P6. Okay, so exhaust pressure. Okay, and that will vary the nozzle. As it opens it, the twitch will open. Once that senses the pressure differential, then yes, it will allow fuel to go in. So if the pilot is selecting nozzle area and the pressure ratio control unit, which senses the difference between P3 and P6, will adjust the fuel flow to suit. So again, normally the pilot will just select the throttle, the pressure ratio control will say, okay, we've asked for extra fuel in the reheat system. I need to open the nozzle. That will sense a drop in pressure in P6. I'll say, okay, that lets me know the nozzle has moved. I can now add fuel in. If the nozzle doesn't move, on selection of reheat, it will automatically cancel the reheat system. It won't allow more fuel to go in, and it will just blow out. And usually what happens is the nozzle will fail into the maximum dry position. Now, it doesn't say in the book, we call an engine without reheat a dry engine. An engine with reheat we call a wet engine, because we make it wet at the back. So rather than have the nozzle stick open and lose pressure, it will fail back to the normal maximum dry position. Okay, basically just become a normal engine. All right. So there you go. There's your CAN box. Afterburner control. You will have a separate fuel pump. You'll have your normal fuel pump for the normal engine. You will also have a separate fuel pump for reheat as well to provide that extra fuel, which will only activate on selection of throttle. Okay, so afterburner control unit, fuel in it. There's your P3 sensor. Okay, back of the compressor, P6 sensor in exhaust. That will sense the pressure ratio difference, and then through oil pressure, through the nozzle pump. Say oil pump, it can be pneumatic as well. It can be air controlled, and normally it's air controlled, but some engines are oil controlled, but some are air controlled. And it will move. I might highlight these colours actually. These nozzles to move in or further out. Okay, so initially it will twitch out, which will decrease the back pressure. Fuel go in, and then the nozzle will match the pressure and continue to move until it goes to maximum. Okay. What I'll do after lunch, I'll dig out a video and let you see reheat actually working. Okay. Any questions there?
Yeah. Once again, please explain dry engine and wet engine.
Yeah, it's not in your book. It's just a bit of knowledge. It's a terminology we give to if you don't have reheat attached to an engine. So a basic engine that doesn't have a reheat system, we call that a dry engine because there's no extra fuel being put into the exhaust, okay, to make reheat. If we add a reheat system, we used to call it a wet engine because it had a normal engine and it had a reheat system as well. Okay, so it was just a bit of terminology. It's not in your books. Don't worry about it. It's just a terminology you might come across. Okay, so you can have an engine with reheat system that's not activated. We just call that normal engine, the dry engine. Okay, it's just normal. It'll work as normal. As soon as we activate reheat, we call that a wet engine. Okay, just a bit of terminology. But I say it's not in your books. It's just a bit of background knowledge for yourself. So don't worry about that. Okay. Any other questions?
Not yet. Only waiting for 100 questions.
Oh, the suspense, yeah. Right, I think it's food time. Yeah, hungry? I am.
Okay.
Okay, let's go for some food and we'll see you in about an hour's time, okay? See you then.